Take one.
Go.
Okay. My name is John Koss. I'm taking Darren's place. He usually is going to do the introduction to our project. Basically what he would say is, in industry, some of the machinery that is used tends to vibrate and become unbalanced. For instance, perhaps a grinding wheel or something of that sort. When this happens, this unbalance can cause problems. So to remedy this problem, we're going to develop a system or a rotating wheel that will correct the unbalance. Now, initially we would have, as you can see our wheel here documented or pictured here, we would have a wheel which had 4 inner and outer chambers, whereas this one only has 1. It would have 4 and 4 control motors. Therefore, the wheel and the system, the shaft it's mounted to, if it was out of balance, in any place it would be out of balance, the wheel could let the fluid through to the different chambers and correct the balance. Now the idea behind this is to have an inner chamber with a motor and a little lever arm that moves back and forth and lets fluid into the chamber to balance the wheel as it rotates. Our scheme of things is pretty much going to go like this. We have our wheel over there. Oops, sorry, I'm rolling over again.
Go.
Our wheel, which you see over there, will be in this part of our control circuit here. From that there will be an accelerometer mounted on the bearings that will pick up the vibration. A low-pass filter will then filter out any extraneous noise and leave the signal that represents the out of balance, which would be at the same frequency as the rotation of the wheel. This signal would then go into a full-wave bridge rectifier, where it would be rectified into a DC signal, and that DC signal would be our error signal. Now in this part of the loop, we are going to be controlling the to determine the balance and if we should open or close the valve to let more fluid into the rotating, into the outer chamber of the rotating wheel. This could be controlled, or in fact in later designs probably will be taken, our part will be taken place by a computer, an HC11 microprocessor or what have you, but for the most part today we're just going to be in here determining whether to balance the wheel or not. For some more detailed description on the fabrication of the wheel, Dave's going to come up here and explain how we went about doing that. I will let him take care of that.
My name's Dave Wiskevich, and I'm going to talk about the design and fabrication of the wheel. Now, the initial parameters we had for the wheel were, we wanted to try and make it around 6 inches in diameter, and we wanted to try and shoot for around 8 ounces volume for the inner chamber. We fooled around with some dimensions here, and we found that in order to obtain 8 ounces of volume, we'd have to make the wheel approximately 8 inches in length, and we felt this would be too long, be more cylinder-like than wheel-like, so we decided to just cut it off and make it 5 inches and live with whatever volume we could get out of that, which turned out to be 4 to 5 ounces. Once we had that stuff done, we had to consider some other things, and the first of which was how we were going to mount the motor to the wheel. For that, we came up with this idea here, which is basically we used a 1-inch outside diameter solid rod. We bored a hole out in the center to the OD of the motor, and we had a cap on the back here which would lock on to 2 flat surfaces you see here on the back of the motor. The next thing we had is the design of the, came up with this idea here. This is basically just a brass shaft with a collar on the top and a set screw to secure it to the motor. And on the bottom part here, we're going to attach a toothbrush tip. This would operate as shown on the bottom here. This is the toothbrush tip, and this would move up and down here to open and close this hole. We arbitrarily decided to just make the hole between the partitions here 1/8 of an inch, simply because it just happened to work well with our toothbrush idea. The last thing we had to consider was a method to empty the water that we let out into the outer chamber back into the inner chamber. For instance, after we had completed some testing. For that, we came up with this idea here. Now this worked because while the wheel's rotating, the water will get thrown out to the outer edges of the reservoirs as shown here. And while that's occurring, there would be no chance for the water to flow back through this tube here. And then once the wheel was stopped, the water would flow back down, and we would be able to empty it back down through this tube here. That's the last thing we had to consider, and at this point we pretty much had everything down that we needed to as far as designing the wheel went. At this point, we took a trip out to the plastics company who we thought initially was going to make this thing for us. We had found out from them, however, that they actually didn't do any fabrication type work. They simply sent it out to be done at a machine shop. Upon hearing this, we figured if that's what they were going to do, we could just as easily do it here in our own shop. And it ended up, that's what we did. We felt we could better follow progress of the project and make changes if we ran into any problems and stuff like that. So we decided to just make it here in the school shop. The next thing we had to do was obtain materials. We had a couple problems there. Main one, which was finding the tubing that we needed to that would form the outer portion of the wheel. We pretty much called all the plastics places around, and none of them had anything in any sizes that we could use. Fortunately, it ended up I was able to get a short section of tube from one of my relatives. It was a little bit larger than what we had initially wanted, but it was all we could find. We also had problems trying to find the tubing that we were going to use to form the partition between the chambers. We ran into the same problem there. We weren't able to. No one had any of the sizes, or if they had anything in any of the sizes we could use. So it ended up for that we just used PVC tubing for that piece. At that point, we started fabricating the wheel. We ran into quite a few problems there. Probably the main one was resulted from a plastic, or I should say imperfections in the plastic. The tubing wasn't perfectly round. The wall thicknesses were not uniform, so we had to make a lot of corrections and stuff on the way there. Also, the PVC tube we used to form the partition between the chambers. Once it was cut, it didn't hold its shape, and it relaxed. So we had some problems with that. We also had problems with the bearings that the shaft would rotate on. They didn't turn smoothly. We had problems lining them correctly on the risers. In conclusion, making the wheel required a lot of exacting work. We did almost all of it ourselves. We learned a lot. Required making we had to do a lot of tweaking and correcting of things to make parts fit correctly. That pretty much sums up the mechanical aspects of the project. And now John's going to come up and discuss the rest of the stuff here concerning the circuitry.
Okay, primarily now the rest of the presentation will be on the external components, external to the wheel. If the wheel is unbalanced, it will produce or generate a signal in the accelerometer that will, well, it should be up here, but it's not. Okay, anyhow, will generate a signal that will look like a sine wave, except there will be a lot of high frequency components on top of the sine wave. A lot of that arise from the bearings and various aspects of this wheel that are parts that are moving around. What we want out of it is we want just the unbalanced signal, which should be a nice, clean, crisp sine wave. In order to obtain that, we will pass the signal through a low-pass filter, which then should give us the nice signal that we want. To elaborate a little bit more on the filter, we needed a low-pass filter that would pretty much pass the fundamental frequency of our rotating wheel. Now we had to do some initial calculations to determine how fast the minimum speed of the wheel would be in order to keep all the fluids tight against the outside partitions of our wheel. That was determined to be about 200 RPM. To be safe, we'd rotate the wheel at about 300 RPM, or an equivalent of 5 cycles per second, or 5 hertz. Now, knowing that all the high frequency components, other than the 5 hertz, we want to attenuate, we made the end of the pass band at 5 hertz and then decrease with an N order of 5. The filter is a fifth order. Arbitrarily, I picked some values here: 0.5 dB for the pass band and 25 dB for the stop band. Again, this is in attenuation on the y-axis. After taking the design of the filter and scaling it and plugging in the components into a splice deck, I plotted out the output, which verified that the design of the filter was correct. In fact, you can see that at this point, which is approximately 5 hertz, we have a 0.2 dB attenuation, and then again at right around 8 hertz, we have a minus 31 dB attenuation. So the filter, in fact, does work, as it is supposed to. Going back to our block diagram, we will see that the output of the filter will then, according to our control circuit, have to be rectified to a DC component. I'm not going to elaborate on the full wave bridge rectifier. That's pretty straightforward. The DC error signal will then indicate to us how much out of balance is being generated by the wheel. Then we can pulse or control the valve on the wheel to determine or to control the unbalance and decrease our error signal. So I'd like to elaborate a little bit on the control circuit. Our control circuit is primarily made up of two 555 timers configured in the monostable mode of operation. When I mean monostable, I mean that they are one shot, they each put out one pulse, and then that is all. The control circuit for the motor is just a simple H-bridge circuit. When the switch 1 is depressed, it pulls the number 2 pin of the 555 timer low. When this happens, an output, a pulse is generated. This pulse is then fed into the bases of the two A transistors. When this happens, the transistors are saturated, which draws the current from the 12-volt supply through the motor in this fashion. This timing circuit at this point will be off, so these two B transistors will be cut off. At the end of the pulse wave, as it starts to fall, it triggers the second 555 timer, which again generates a positive pulse. This positive pulse will be led back into the B bases the bases of the B transistors, which will then be in saturation and draw current back in the opposite direction across the motor. The final pulse wave will then be a pulse with positive and negative directions. The duration of the pulse can be controlled by the 1 mega ohm potentiometers. So that pretty much concludes the entire circuit that we have so far. I would like to direct your attention over here to our rotating device, our wheel. I'd like to point out that there are some fins on the exterior of the wheel. Initially, we designed the wheel to be rotated by air so that it would not produce any extraneous vibration. When we did test the wheel out, we did have fluids in the inner chamber, and they were passed from the inner chamber to the outer chamber as it rotated. Because we did not want to fully glue the wheel together, because it would be at that point permanent, and if any other group of students were to undertake the project, they would have no way of taking it apart and modifying it in any way. So in order to prove that the valve does move, in fact, we are going to rotate the motor using a motor in this belt system and control the speed with this rheostat. We will strobe the device in order to see the actual movement operation of the motor valve opening and closing. I would like to do that right now at this point. Okay, as we synchronize the motor with the strobe light, you can go ahead and press the button now. You can see by looking in there that the valve is opening and closing. Hopefully it is. Is it? Can you see in there?
Got it strobing.
You see in there now? What we're doing here is we're just using a control circuit like I described earlier. Here's the control circuit. It goes in through a couple of brushes down here, through the slip rings, and it controls the motor. I don't know if you can get a good look at this motor. It's about 1.25 inches long, about a 1/2 inch in diameter. That's including a 64-to-1 gearhead with nylon gears. The torque is phenomenal on the motor. It's simply unbelievable. It rotates, the motor itself rotates at about 15,000 RPM. You can see our brass bushing. There's our fluid seal in there. How the two seals are, how everything is screwed together right here. We got our shaft. We got our counterbalance here. Got our bearings, our risers. This is our power supply to our circuit, and that's pretty much it. See ya.